What is fluid dynamic all about? In the last slides, I showed you some application cases. I showed you how we use fluid dynamic as a tool in scientific projects or in a bachelor thesis. And now we want to have a closer look. What in general is fluid dynamics? You can't see, in many cases, you can't see the fluid flow, you can't see the movement of water, or you cannot see the movement of air in the sky. And fluid dynamics, or fluid dynamics is also called fluid mechanics, and this is in general the science of resting and moving fluids. Resting fluids. Resting fluids, for example, if you have a liquid fluid, it is the science of hydrostatics. Yeah? You need this if you want to build a dam or a bridge. Or resting fluids can be aerostatics, like gases. And fluid dynamics also includes the science of moving fluids. It's getting a bit more interesting than resting fluids. And moving fluids can be the science of hydrodynamics, if we have a liquid fluid like oil or water, or it can be the science of aerodynamics, like gases, if the fluid is a gas. Yeah? Where do we need aerodynamics? I think you all know it. For example, if you have an airplane or a propeller, it deals with aerodynamics. Okay. Where can we find fluids? Where can we find fluid flow? We find fluid flow in many applications, not only in techniques, but also in other subjects of science. For example, in medicine, the flow of blood through the veins or through the heart or the lung is fluid dynamics. Or here, if you look at this piston engine, the fluid flow of gas inside the piston engine has to be calculated, has to be examined, or even the fluid flow of diesel or gasoline fuel into the cylinder deals with fluid dynamics. Or for example, we have an airplane or windmill or car geometry, that's all topics of fluid dynamics. What is fluid dynamics in general, and what is the history about fluid dynamics? How old is it? And I can tell you, the topic of fluid dynamics is a real old topic. Even the Romans or the Greek or the Egyptian built fluid dynamic vessels, ships, yeah, even, but up to the 17th century it was more or less experimental work. Yeah, the people built water basins, water channels, wind tunnels, but most of them were experimental. From the 17th to 18th century, many physical laws have been, let's say, invented or examined, and for example, mathematical formulations or theory laws about fluid flow. Some important scientists like Bernoulli or Torricelli invented a lot of theory to make calculations for fluid dynamic problems. And from the beginning of the last century, let's say from the 1560s up to the 70s, the first applications in numerical simulations of fluid dynamic problems started. Here we deal with computational fluid dynamics, and the computers get stronger and stronger. We get more powerful computers, and that's why even fluid dynamics problems can be solved in a better way. So what is in general computational fluid dynamics? CFD. Maybe you have not heard about CFD before, but I'm really sure you all have seen results of computational fluid dynamics and you all know what it is. A good example for computational fluid dynamics is the weather forecast. Here in this weather forecast table of Europe, we have Spain here, Germany, France, we have Norway, Russia, and all the other European countries. And what you see on this picture, you see first, of course, the temperature here in these regions. You see if there is sun or rain, and you even see pressure fields. Yeah? Deep pressure fields. Here you have high pressure fields. And you see velocity of the air, that is the wind. And all these results are calculated for the next day or for the next week. And that's what computational fluid dynamic is about. Yeah, now look a bit closer. That's the same map. Here we have Spain, Germany, France, Italy, Great Britain, Iceland. And if you are a little bit, if you know how to read this weather forecast, or if you used to look at it in the news, yeah, you know in Central Europe our weather is influenced by two main factors, more or less. It's not always like this, but in many days, even in summer, it's really obvious. We have these islands here, the Azoren, and in this region we always have really big pressures. And what you see here on this map, there are lines, and we call these lines isolines of pressure or isobaric lines. And on this line we have everywhere the same pressure. Also, it really often happens that we have low pressure here in Iceland. So you see high pressure at the Azoren Islands and really low pressure at Iceland. So what will happen? We have high pressure here, low pressure here, and you all know it from maybe, yeah, if you make a hole into your bicycle wheel, yeah, what happens? With high pressure inside the wheel, low pressure outside, the air will come outside. And the same happens also here in Europe. The air comes from the low pressure side to the high pressure side. Here we see it, yeah. The air, the wind will go to Iceland, and what will happen if the wind comes here from this African region and will go to the north, it will also go here from west to east, and that's why we have relatively good and warm temperature here in Europe. So, where else can we find fluid flow? How can we see fluid flow problems? Here's a picture, and this picture is really seldom. It shows a supersonic airplane, a jet, and when the jet reaches a really high velocity, we get condensation of moisture inside the air because of the low pressures above the wings. Or, for example, where else can we find fluid flow in nature? Here we see mountains, we see a glacier, and we see glacial movement of the ice down the hills into the valley. And this is also fluid flow. So really fast phenomena can be fluid flow problems, or really slow phenomena in nature can also be fluid flow problems. How can we solve such a problem? And maybe you know this slide from your physics classes. It's always the same. Yeah, we have a problem in physics, or in a technical problem, or social problem, and then we must make some experiments, and from these experiments we get observations and results. And now if we collect these results, we can go back and look if they solve our problem. And if we say yes, we solve our problem, we realize the solution. And if we say no, the results are not useful for us, we can go back to the problem and start the cycle again. So, for example, why does an airplane fly? That's a good question. Yeah? You have to design the wing, and if you just look at the wing and design it like you've seen somewhere else, it can be wrong. You have no understanding of the physics, you do not know why you do these things, so you just try, like trial and error, and you can get wrong results. So why does an airplane fly? It flies because it has a lift force upwards and a drag force here and a gravitational force, and the lift force must be bigger than the gravitational force. Then it flies. Yeah, here I show you some history of airplanes, that this was not always so obvious in history. Yeah, planes are not so old, ships are really old, yeah, or propellers are somehow old, but flying planes, let's say 150 years, yeah, not much more. And so the innovation in this time was really fast. Innovation in the last century. Here on this picture you see 4 different planes from 4 different ages, here older one, newer ones, and the development of airplanes was really rapid in the last century. Yeah, here you can see something about airplane design. Yeah, also on this slide, I don't want to talk too much about it, but if you go to the slide, if we refer to it, you can see some interesting movie about airplane design and solving of fluid flow problems. Let's go a bit faster over this slide. Yeah, and not only in the development of airplanes, fluid flow was really important. It was also really important in car development. Here you see an older car model, yeah, has a geometry like a box, has a really bad fluid flow behavior. And here you see some newer sports car design. It's a faster car, and you can also visualize fluid flow around this car geometry, and so you can have a development. This was the first step. This was the second innovation step. Yeah? They changed the geometry based on fluid dynamic problems. So we are in the problem. We have the problem. Yeah, if you go back to this slide, you see normally you see the cars. You see they move in the air. But what you cannot see this fluid flow behavior because the air is invisible. So a big topic in fluid dynamics is how can we visualize fluid flow, or why should we visualize fluid flow problems? Because we want to see it. We want to see if our examinations, if our if our experiments are right. Yeah, we have to see it, or we have to measure fluid flow. One way to measure fluid flow here, for example, if you have a car and you have a wind tunnel, and we know the air is about 60 kilometers per hour fast. What can we do in the wind tunnel? For example, we can make a force measurement here. We have a rope, yeah, over a roll, and here we have force measurement, maybe spring, and then we can measure how big the force is. Yeah, that's also one of the important topics. If we have a wind velocity, if we have fluid flow, we always will have a force on the car or on the plane or on the object or on the house. And this force, this wind force, can be really high. So you can, maybe if you ever heard about hurricanes or great thunderstorms, then you know the forces of the fluids can be really high, and they can damage houses or objects. Yeah? For example here, depending on the wind velocity, we have a so-called drag force, and this drag force acts on this tree, and if the drag force is too high, like in a thunderstorm or in a hurricane, you can break the tree and damage it. Yeah? For example here, we have a good picture of a damaged tree after a thunderstorm, and so you can estimate that the forces we get only from air movement can be really high and dangerous. Or for example here, we have a roof of a house, and the construction was not so advanced, so we damaged this roof only by influence of moving air.